Dear all, a very good day. In the present lecture, we are going to consider power and area consideration. In the previous lecture, we have seen the noise margin and noise immunity regarding the inverter circuit, and before that, the critical voltage levels were discussed. Now, in the present video, we are going to discuss very important consideration, that is power and area. How both of these factors play an important role to decide the working or size of the transistor and different aspects how our integrated circuits will function. Okay, so there are two more important issues that play a significant role in inverter design. First is our power consumption, and second is the chip area occupied by the inverter circuit. Okay, now about 1 million logic gates can be accommodated on a VLSI chip using 0.5 micron MOS technology, and the circuit density is expected to be increased. This is a very old data. In the present time, we have successfully been using 22 nanometer technological node, and at least 10 million to 50 million logic gates can be accommodated on a single VLSI chip. Okay, following the Moore's law. So this increase in the technology is getting to us, but however, with the reduction in size each and every time, that is from 5.5 micron, approximately 500 nanometers to 22 nanometers, sizes reduced considerably, and at the same time small geometry effects have played their role. Those who are master's student, they will definitely understand how much importance small geometry effect plays in our functioning. Okay, so power and chip area are very important. By reducing the size of the transistor, we are able to reduce the chip area. So how will this affect the power? Okay, and why power is important consideration, in brief we are going to look here. Now, since each gate of the chip dissipates power and thus generate heat, the removal of this thermal energy, that is cooling of the chip, becomes an essential and usually a very expensive task. Okay, as more and more transistors are accommodated, so more and more heat will be produced in the devices, and removal of this heat or cooling of our device is a very complicated task and essentially useful. Okay, so if we are going to look at the junction temperature at any point, it is given by Tj, that is junction temperature, that is equal to Ta ambient temperature plus theta P. Theta is thermal resistance of the material and P is the amount of power dissipated. So temperature is directly dependent upon the amount of power that the particular circuit is able to dissipate. Okay, now the DC power dissipation of an inverter circuit can be calculated as a product of its power supply voltage and the amount of current drawn from the supply during the steady state or in the standby mode. Okay, so there are different types of power, static and dynamic power, and different reasons for it. Okay, so when our circuit is not performing anything and it is in an ideal mode, we want that very less amount of power should be drawn from the circuit. However, when it is working or switching its states, then it will consume some power. Okay, so DC power dissipation of an inverter circuit can be calculated by the product of its power supply voltage and the amount of current, that is P power. For the calculation of power, simple V into I formula has been put up here. Okay, or relation between V into I can be looked up. You know, I square R is the formula for power. If you will convert it to, so if you will convert it properly, you will get a proper formula for power. Okay, so the deep micron technology, the increase in subthreshold current causes the power consumption in a standby mode. Thus, it will shorten the battery life unless a thread can be reversed in novel circuit design or system technology. Okay, so small subthreshold, or you can say small geometry effects, do creep in as the device size is further reduced. So in deep submicron technology, subthreshold current causes more power consumption. Okay, so as the device size is reduced, so electrons can even at a lower voltage, electrons can often gain energy and produce current. So before the threshold region also some current will flow, which will result in, it can be minority carrier current, small majority carrier current, which will result in power consumption. This current may be lower as compared to previous devices, but since the device size has now been reduced, this current can play a significant role. That's why we are worried about this current, and it will directly impact the battery life. Okay, so power in the DC form can be given as PDC is equal to VDD into IDC, that is drain current and the supply voltage. Notice that the DC current drawn by the inverter circuit may vary depending upon the input and output voltage levels. Yes, particular input and output voltage levels will also decide how much current a particular circuit is taking from the supply voltage. If the circuit is switching its characteristics and the voltage is somewhere between VIL and VIH, then it will consume more current. Whereas if the circuit is stable at logic 1 or at logic 0, so normally drain current does not flow. So at this time power will be very less, power consumption will be very less, because current flow is less and only minority current will be flowing in this condition. So depending upon the current conditions as well, it depends what is the power of our circuit. Okay, to reduce the chip area occupied by the inverter circuit, it is necessary to reduce the area of MOS transistor used in the circuit. Okay, so we want to reduce the chip area occupied by the inverter circuit. So we will have to reduce area of the MOS transistor, and this is possible only by reducing first channel length and second channel width. These are the most important parameters. I have in the starting of this video mentioned that we are looking at 22 nanometer technology. So this 22 nanometer is actually the length of the channel, and MOS transistors in the present date are specified by the length of the channel. Okay. Thus, the MOS transistor has the minimum area when both gate dimensions are made as small as possible with the constraints of a particular technology, because again small geometry effects will creep in. There will be, in the smaller dimension, electrons will get higher energy at less voltages, and they may show effect like punch through and IDBL, and there are other effects which do play a role. Master students will do know this. For a bachelor student, only the name of these small geometry effects is sufficient for the time being. Okay, thus the MOS transistor has a minimum area when both the gate dimensions are as small as possible with a technological node. Okay, it follows that the ratio of the gate width to the gate length should be as close to the unity as possible in order to achieve a minimum transistor area. So the aspect ratio should always be near to the unity. This requirement, however, usually contradicts other design criteria such as noise margin and output current. Therefore, a fixed value of W by L is taken, and even the ratio of W by L of load and driver transistor plays an important role, as we will be looking in subsequent lectures. Okay, this is for the present video. In the next video, we are going to look at resistive load inverter and so on. Thank you.